This is going to be my workshop on computational chemistry for the Grotron group. And most of my work is with Q-Chem, so that's what I'm going to be talking about. I'll try to show some relations to Gaussian, but yeah, mostly going to be talking about Q-Chem. So Q-Chem has two components. You have Q-Chem, which is the software that performs the calculations, and then IQmol, which is the software where you can build molecules and look at the results. And then to run calculations, you need to use a terminal because Q-Chem is only on servers at our school. So you need to use a terminal to access those servers and start the calculations. So to get started, I'll just give a tour through IQmol. And I'll try to build our published catalyst, this ruthenium terpyridine phenanthylene sulfonate. So when you start, open up IQmol. This is kind of what it'll look like. You'll have this pane on the left side, which when you add molecules, you'll be able to see them here. You have your drawing space, and you have all the building commands up in the top, as well as like various calculation and other menus. So to start off, I usually don't like this blue background. So I'll right click on the background, edit color, and I usually go for like a gray color. If you do black, kind of looks nice, but the mouse sometimes gets hidden in the black. And then if you do white, the hydrogens kind of get obscured. So gray colors is decent. So just change it to a gray color. So to start a new molecule, you'll click this page here, and you get this untitled project here. You can build a bunch and select the molecule you want to work on by selecting and unselecting the pages on the left. So we have our untitled here. We can, we'll go ahead and start building. So there's various ways to build. You have, well, to build in general, you want to have this hammer and screwdriver selected. And that puts you in build mode. And you can build with one of these three components. You have the element selector, where you can select the various elements and add them to your page. You have the fragment selector, where you can either select a functional group to add, or you can select a molecule. And IQmol has tons of different molecules pre-built in that you can select. And so it makes things a lot easier when you're trying to build molecules. It doesn't have metal-based molecules, which we use a lot in our group, so you'll have to build those yourselves, but at least you have the building blocks here to start building your molecules. And then you have this add hydrogens button, so if you have carbons that don't have hydrogens, it'll add those to fill the coordination environment of various atoms. And also that could be useful to know if you've left some atoms unsaturated and whether you need to change what you have or not. So let's go ahead and start building the published catalyst. To do this, I'm going to start out with a phenyl group, or actually I'll add a benzene ring. So we go down to aromatics under molecules, and we can add benzene. And I'll just add this here. And so we want to add 2 more benzene rings to this group. So what I'll do is remove this hydrogen here, so we can build off of this atom. And we can add our functional group of phenyl. So to build the phenyl off of this carbon, we want to select the very middle of the carbon, and we can add the phenyl group. And then we'll want to do this one more time on the other phenyl to add the second ring. And one thing to note is if you don't select right on the middle of the atom, you'll kind of drag around. It doesn't have a very big click window, so you want to click on the very middle. And if that doesn't work, you can go back into the build mode and select what you want again. Sometimes it'll be in a different mode even though it says it's selected. So you would just go back and go to build mode and select your fragment again. But now we have our triphenyl system. We then want to make these nitrogens. So, oh, I didn't talk about the selector group. This magic wand symbol allows you to select parts of your molecule. So if you wanted to select this hydrogen, you would just click and drag over the hydrogen. And if you wanted to unselect something, say you accidentally selected this atom, you right click and drag and you can unselect it. So it makes it pretty easy to select what you want. So I'm going to select and remove these hydrogens. And now we want to replace these carbons with nitrogens. So go to the build mode, select carbon, or select the atom, and then we click nitrogen. And we could just click on these atoms. To turn them into nitrogens. And it's going into select mode, so I have to go back to build mode and click the nitrogens. Okay, so this is our terpyridine. As you can see, it looks a little bit skewed. So something we can do to make that a little bit better is click this minimize energy button. So this will use like forces, just basic forces to minimize the energy of the molecule and put it into like a more ideal shape, which will speed up your geometry optimization calculations a lot because the initial guess is a lot closer to what it should be. So if we have this skewed shape, we click the minimize energy and it will bring it into a much nicer terpyridine type molecule. So now we have this. We want to make our phenanthroline group. So again, we'll go into build mode, select the molecules, and there's this polyaromatic hydrocarbons, and luckily they have this phenanthrene built in, so it makes our job a lot easier. So we can select this and put it in. So let's just first turn this into a phenanthroline, 2 nitrogens. So again, we'll remove these hydrogens and delete them using this red X. Go back into build mode to make the nitrogens. Yeah, hopefully they'll fix this selection problem in a future update, but for now, we just gotta deal with how it works. So we now have our phenanthroline. Let's go ahead and add the sulfonate group. So delete this hydrogen and go back into build mode and go to functional groups. And they have this drop-down menu of sulfur groups. And we can select sulfonic acid. So we can add this sulfonic acid to the phenanthroline. And let's go ahead and erase this hydrogen because we'll want that coordinated to the ruthenium. And as you might see here, instead of having 2 double bonds to oxygen, there's 2 single bonds, and that will affect our minimized energy. So to add a second bond to one of these oxygens, we'll go into build mode and select oxygen. We could use oxygen here or sulfur, but if we drag from the sulfur to one of these oxygens, it will make it a double bond. So that's an easy way to go from a single bond to a double bond. And if you want to go from double bond to a single bond, I'd recommend just selecting and deleting the double bond and then doing the same thing to add a single bond. But this should be right. We now have 2 double bonds to the sulfur and a single bond, which will be attached to the ruthenium. So let's sort of get this into a better orientation. We can select our phenanthrene, and you can see here it selected some of the terpyridine, so we'll unselect that. And to move this around, to move it translationally, you press Control and drag it with right click. So that gives you translational motion. Control right click, and to rotate it, you do Control left click. So now we have it sort of in the right space. We do Control left click, and we can rotate it. And for rotation, it can be a little confusing. The way that I like to do it is always go to the direction you want to rotate it. Like say you wanted to rotate it to the right here, instead of trying to rotate it to the right, angle it towards you and then rotate it this way. It makes it a lot easier to rotate. So now we have all of our organic components in a somewhat reasonable orientation. We'll go ahead and add our ruthenium. So we'll go, first we'll unselect all. Another way you can unselect all instead of using the wand and right click, you can do edit and select none, and that'll unselect everything. So now we want to add the ruthenium. So atom, build node, atom, and ruthenium. And we add the ruthenium by dragging from one of these nitrogens. And in order to use minimize energy, the bonds have to be in place. So if we just left it like left it like this and minimized energy, it would not give us an ideal shape because these bonds are not they're not in place yet. So we'll want to draw in all these bonds to give it octahedral coordination, and then the minimized energy will put it into the octahedral point group. So to make all the bonds, we'll use the ruthenium and drag from the nitrogens. And it is a little finicky, I guess, to draw these in. Yeah, best thing is to go from the very middle of the atom. And sometimes you just have to redo the build node.
So if you're trying to make like a normal, like in this case, a nitrogen ruthenium bond, we have to have the ruthenium atom selected?
So in order to make the bond, yeah, you either go from the nitrogen with the ruthenium atom selected and drag to the ruthenium, or you could have a nitrogen selected and drag from the ruthenium to the nitrogen. So,
okay, gotcha.
So here we can go from ruthenium to the nitrogen and just drag it over to the nitrogen that way. I would use ruthenium in this case just because it's less steps. You have to do a separate one for the oxygen, but it's only one extra step. It's not really a big deal.
Okay, gotcha.
See, now I would have to click oxygen and then go do the same thing to the sulfur. Okay, so now we have 6 bonds to our ruthenium center. Doesn't look very good, but if we click this minimize energy button, it should give us our desired molecule. Sweet. I think that looks good to me. We have phenanthroline connected to the ruthenium and the terpyridine connected to the ruthenium. And say we wanted to do a variation of this. Say we wanted to compare the energy of this with the water to the with the ruthenium connected to a water compared to ruthenium connected to the sulfonate. We can add a water molecule, draw in our bonds. And then we would remove the bond to the sulfonate. And we can, from here, we can go to minimize energy, and it should change the orientation to a reasonable orientation with the water coordinated as opposed to the sulfonate. So here it looks good. However, if you wanted to make this more chemically accurate and get a better guess to the optimized geometry, you would want these protons facing towards the sulfonate. So something you can do is select the water molecule and rotate it using the same as you would a fragment. Control right click and orient it more that way. I'm just going to rotate it by going facing towards the angle I want to rotate. Control left click and drag it this way. So it's a little bit better. From here, we could do minimize energy again, and it should make those bonds a little bit nicer. One other thing I wanted to show, so say you, from literature, you knew that this distance was like 1.8 angstroms. You can set that by selecting the two atoms and going to build set geometric constraint, and you'll set this to 1.8 angstroms. And again, because it's in a ring system, it won't let me. So just as an example, I'll delete this and then we can set it this way. And it'll move the water so that this is 1.8 angstroms. Sometimes it'll move things you don't want to move, like saw how the oxygen moved as well. It's not always the best solution, but for some solutions, that's the best thing you can do. And yeah, in this set geometric constraint, there's also other options that I'll go into more depth next time. But use this for bond angles, dihedrals, and bond distances. So it's the same method, you just have to have the right thing selected. If you want to constrain your calculation, you click this constrain button, or scan between a number of distances, you can click the scan. But I'll talk about this more next time. The scan is usually better if you just do each distance individually. But the constraint is really helpful, especially for like transition state calculations. But we won't worry about that today. Just know that you can set an angle, a dihedral, or a distance using this set button. Okay, so we have our molecule that would be a decent guess for performing a geometry optimization calculation. And to set that up, you go to calculation, Q-Chem setup, and this is where you can use the GUI to set up your calculation. But before that, I want to talk a bit about the types of calculations you could do. so we know what to do when we're setting up our calculation. So there are three major types, or three very common types of density functional theory jobs. The geometry optimization, which is used to find the optimized geometry of the molecule based on electronic structure, not just atomic forces. And anytime you do any type of calculation, this should be the first step you do, is do a geometry optimization first. And then once you have your optimized geometry, you can do more advanced things like single point energy, frequency calculations, and even other things like the transition state and time dependent, or TD-DFT and other things. So geometry optimization will give you the electronic energy of your molecule, but I recommend doing a lower basis set and functional for the geometry optimization, and then doing a higher, a more accurate functional basis set combination with single point energy. This will also give you the electronic energy of the molecule, but it's a lot faster than a geometry optimization, so you can use higher levels of theory. You can also do, after geometry optimization, a frequency calculation, which will tell you all the vibrations that are occurring in your molecule, and also gives you the entropy and enthalpy of the molecule in its ground state, so you can compare your Gibbs free energy to other states of the molecule. So if you want to get a full energetic analysis, you have to use a frequency calculation. In Gaussian, I often see people do optimization and frequencies together, and you can do that with IQmol too, but I highly recommend separating them out, because if your frequency calculation fails, you won't get the results of the geometry optimization. So it's better just to do them separately. That way, if this fails, you can start from your optimized geometry already. So yeah, you can also do transition state calculations, TD-DFT, to find absorption spectra, but I'll talk about those more in our next meeting, hopefully. One thing to note is that the actual energy value you get for your molecule, it doesn't mean anything unless you compare it to another molecule. So the energy has to be compared to another molecule, and the other state of the molecule has to have the same number of atoms and has to be done using the same level of theory. So you couldn't add a water and reasonably compare the two states of the molecule. For certain situations, you could have the energy of a water and the molecule to a water and the molecule together, but you really have to be careful about your calculation, about the type of calculation in order to do that. So yeah, main point is the energy is only relative. So the absolute energy that you get doesn't really mean anything, because you could use a different basis set and it'll give you a totally different energy. And another thing to note is that the different types of calculations you do not need to be of the same level theory. So as I said before, you could do geometry optimization with a low level of theory and then move on to single point energy or frequency calculations with a higher level of theory. Frequency calculations, especially for large molecules that we use in our group, they take a long time, so you don't want to use too big of a basis set and functional. But yeah, it doesn't have to be the same as the optimization. So when you're doing DFT calculations, the computational cost and accuracy is mostly determined by two things: the functional and the basis set. So the functional tells you how the calculation is performed, whereas the basis set tells you the number of coefficients, the number of terms used in that functional. So you can have a highly accurate functional using a small basis set, or you can use a less accurate functional with a really large basis set. Probably the former is the better way to go about it. But you want to have as high of a functional and basis set level of accuracy that you can get while having a reasonable computation time. So the more accurate these are, the more time it'll take to do the calculations. So picking the functional and basis set can be quite complicated. There's two ways you can go about it. The easy way to do it would be to look in the literature and find someone who did a calculation that's similar to what you want to do. So similar molecules, similar piece of information that you want to get out of it, and just copy their functional and basis set. The more difficult way to do it is to look at the research that compares the functionals and basis set accuracies and determine which component is most necessary for your calculation, and use the functional basis set combination that gives you the most accurate for that type of calculation. So on the left here is a graph done by Medrosian and Hedgordon. The reference is at the bottom here, where they compare a bunch of different functionals for various types of calculations. One that we commonly use is thermochemistry. So that's these two groups here. And as you can see, as you go further down, these functionals have a lower error. And so these would be ones you'd prefer to use over these ones that have a higher error. And as you can see, B3LIP, which is one of the most commonly used functionals, actually has significant amounts of error for these types of calculations. So I recommend, although many people use B3LIP, looking at these functionals with lower absolute error. One that Dr. Mal recommends a lot, and I've had very good success with, is this Omega B97X-V. It takes a reasonable amount of time for calculations. So for things that are like 65 atoms, I can get these done in a few days to a week for a geometry optimization, and similar for a frequency calculation. If you go larger than that, I've done like 120 atom calculations. This can drastically move up in time. I've had them frequency calculations take up to almost 30 days. So for something like that, you might want to go to something a little bit less accurate. So there are other things you would definitely want to add to your calculations beyond just the functional and basis set. One of these things is the electron core potential, which you have to tell Q-Chem to use an electron core potential, and if you don't tell it to use it, it'll just calculate the core electrons in a standard way, which will take significantly more time. So what this really is for larger molecules, say you want to use ruthenium, the electron core potential will, instead of calculating the electron energy of each electron in the ruthenium, including all the ones in the core of the atom, so the ECP will calculate those as a standard potential rather than trying to calculate the electronic state of each of those electrons. So in a ruthenium, all of those core electrons won't change very much. It's only the valence electrons that really make a difference in the calculation. So if it replaces the calculation of those core electrons with a standard potential and only calculates the valence electrons, your calculation will be performed in a significantly lower amount of time. So anytime you want to use like a metal, definitely use an electron core potential. And it's pretty simple to add, especially for many types of basis sets. Certain basis sets don't have an electron core potential, so you have to use a split basis set, using different basis set for like carbon, nitrogen, oxygen, hydrogen. from the metal basis that you use, I'd recommend you can do that, but it's a lot easier and more time efficient just to use a basis that has calculation for metals with an ECP and for the other atoms like carbon, nitrogen, oxygen. A lot of calculations you would want to use a solvation model, especially when the solvent is very important for the reaction you're trying to simulate. So like for water oxidation, you're going to be performing the reaction in water. So you want to add a solvation model that creates a polarizable field around the molecule that allows for the creation of dipoles that are similar to water for the construction or calculation of your molecule. So even for other types of reactions, say you have a catalysis reaction that performs really good in a certain solvent, you could compare how two different solvation model or one solvation model with two different solvents changes the energy of your molecule. And also it'd be best to replicate the states of the reaction using the solvation model. And yeah, a lot of solvation models use this polarizable continuum model. That's the one I know most about. It essentially makes a surface around your molecule that can be polarized. There's more advanced types of solvation models, but they end up taking a lot more calculation cost. So yeah, PCM models are generally the best for our types of calculations. There's CPCM, which is the default in Q-Chem, which is a little bit lower quality. SMD model is a higher quality model. Probably want to use SMD, but it does make the calculation a bit slower, especially for frequency calculations. For those you might, if those take a long time, you might want to switch to CPCM. One final thing that you might want to add for certain functionals is a dispersion correction, especially with B3-lip. There's no calculation of dispersion forces. So when you have two atoms that are very far apart, there's it only calculates the electronic interaction. It won't calculate like dispersion forces, which could be very important for larger molecules. So if you're using B3-lip, you want to add a dispersion correction. The functional I mentioned earlier, omega B97X-V, does have dispersion correction built in, so you don't want to add that in afterwards, because then you're double accounting for dispersion correction. Probably the best dispersion correction you could use is Grimm's D3 correction with Beck-Johnson damping. There's other ones you could use, but this, for now, is probably the best one you could use. So let's go into making our calculation. So we have our atom here. We go into calculation and do Q-Chem setup, and this is where we can set all of the variables for our calculation. And on the right here, it'll show you what the input file looks like based on the variables you set. As you become more advanced with Q-Chem, you don't need to use this GUI. You can just add the variables as you want. But in the beginning, it's good to just see what the changes look like. And then you could just copy and paste this into your input file and send it straight over. So for this, we'll go ahead and do a geometry optimization. So under the calculate, we can go to geometry. This will be geometry optimization. And as you can see here, this changed the job type to optimization. Other types of calculations are here. You can see frequency, you can see energy, which is the single point energy, and lots of other types of calculations. But for this one, let's go ahead and do the geometry optimization. The method this is the functional that's used. As you can see, V3 lip comes up, and so does omega B97X-V. So we'll go ahead and use this. There are some functionals that are not built into this method, but you can just type it in here to the bottom and use a non-default functional. So we changed our method to omega B97X-V, and as you can see here, it changed it to method equals omega B97X-V. So now we want to change our basis. The basis that I want to use here is not here. DEF2-SVP, that's the one I talked about before. So we'll go ahead and select just a random basis, and it'll show up here. Basis equals 431G, which is the one we selected, but we can just change this to DEF2-SVP, which is double zeta basis set. If you want to make this a little more accurate, you would use triple zeta basis set to TZVP. If you want to go even more accurate, you do QZVP, which is quadruple zeta, but SVP is just fine for geometry optimization. Another thing that you might want to change for your molecule is the charge. Our molecule here should be a +1 charge because it's a ruthenium-2 and there's 1 minus charge. So we'll want to have +1 charge. So we can change this here to +1. And it will change this number here, which corresponds to the charge of the molecule. So at the top of this geometry section, you'll have two numbers. The first is the charge and the second is the multiplicity. So if you change the charge, it'll change the multiplicity automatically for you, so you don't need to worry about it for the most part. So multiplicity for this molecule is going to be a doublet. But say we wanted to calculate a quartet, we can go up 1 here, and it'll do multiplicity of 4. For ruthenium-2, it's definitely not going to be quartet, so we'll calculate it as a doublet. But you might want to change that, especially for transition states, higher oxidation states of a molecule. You definitely want to test out the different multiplicities, because sometimes the triplet or whatever spin state is going to be lower in energy than the low spin variety. So as I said, we want to add an electron core potential. The one I want to use here is also not available, but we'll just add a random one so we can add it to our calculation. The ECP that I'll use here is called DEF2-ECP. And this goes well with our basis set, which changed for some reason, but we can take it back. DEF2-ECP goes well with basis DEF2-SVP. Another thing you'll need to add is ECP fit equals true. This just tells it that you do want to use the ECP. Otherwise, it'll just ignore this ECP section. And especially if you're using a non-standard ECP, you want to have this ECP fit equals true. I think that's correct. Yeah, we'll deal with it for now. And then one final, or a couple more things, I guess. This convergence, you want to have it at least to convergence of 8. So this will tell you how accurately the SCF converges on a specific state. So imagine you have the potential energy surface. If it's a lower convergence value, it'll find somewhere around the bottom of that potential energy surface. And if you increase the value, it'll get closer to the very bottom of that potential energy surface. So recommend at least 8, but you can go higher, you can go lower if the calculation never converges. Another thing that you might want to add is this unrestricted.
Hey, Jake, quick
Yeah,
question.
sure.
You, in your slides, you showed a chart that was like, different, like there was, a model that you chose, it was TCE and TCD. Yeah, correct. These, have you talked about these yet and setting up your parameters? I just want listed
So
functional. Yeah.
these are just different types of functionals. So I just picked one that works for me, omega B97X-V.
That's your method.
Yes, yes,
Okay.
that's yeah, that's how the calculation is performed.
Okay.
Um,
Cool.
in our next meeting, I'll probably talk a bit more about how to pick a good functional.
Mm-hmm.
Uh, sorry. Um,
Okay, cool. Thank you. Yeah, I just wanted to kind of connect this figure to the changes you're making to the whole experiment, so I could kind of just relate them. But I see that how they line up now.
okay, yeah, awesome.
Cool. Thank
Yes,
you.
this one I selected corresponds to this method right here, which is uh, this one. Yeah, hopefully that makes sense. Thanks for the question. Um, so, so yeah, this unrestricted changes how it calculates various orbitals. So if unrestricted is false, it will be restricted, and orbitals that are generally degenerate. Um, so yeah, if you have degenerate orbitals, it'll make all of those orbitals exactly the same energy. This isn't always the case for our metals. So things could be varied very slightly in those. So you have all energy levels at one region. They can vary in energy slightly. So this you would want to use unrestricted equals true or one, which happens if you just click unrestricted. You only want to use this for open shelled systems. If you have a closed shell system, you want unrestricted equals false because it'll start to mess with your calculation. But this ruthenium 2 is going to be open shell system. You want to use unrestricted equals true. So one final thing that we want to add to this computation is a solvation model. So to add a solvation model, we would go over to this advanced tab. And down here, there's solvent model. And we can select from a variety of different solvation models that are default. The one I'll want to use here is SMD. And not only does this add this solvent model to the bottom here, but it'll also add another section here at the bottom. Oh, um, I guess it doesn't add it in the GUI. So I'll refer to one of my calculations. Um, I think the default is water, so that's why it's not adding it here. But you do want to just specify it just cause, and if you want to use anything other than water, you can just change it. So say we were doing our reaction in methanol, we could just change it to methanol. But yeah, here we'll use water. One kind of complicated thing is that if you use a different solvent model, such as PCM, it won't select, you won't be able to select the solvent. You have to select actually a dielectric constant. So here we have our solvent method is now changed to PCM. The type of PCM method is specified in this PCM section. So here it's IEF PCM. And then the solvent section, instead of using a specific solvent, it'll use a dielectric. So 78.39 is the dielectric of water. You will have to look up in the literature the dielectric of other types of solvent if you want to use another type of solvent. So pretty easy to find in the literature, but you just have to find that value rather than being able to just type in the specific dielectric. But SMD is easier. You don't need to do that. You could just type the solvent. So not only is it more accurate, but a little bit easier to use. So probably best just use that. But from here, I think everything should be correct. So we have our molecule section with the charge and the spin multiplicity, the geometry data and the coordinates. We have our variable section with the correct basis, an electron core potential, our job type of geometry optimization, our method of omega B97X-V, an SCF convergence of 8. We have our SMD solvent model, and we're using an unrestricted calculation. One thing I didn't talk about is this GUI equals 2. This tells Q-Chem whether or not it should save the orbital data. So if you don't care about looking at the orbitals, you set this to 0, and it won't save that data, and it'll save space in the output file. It'll be a little bit faster, but then if you do happen to want to see the orbitals down the line, you won't be able to see them. So if you set this GUI equals to 2, you will be able to see the orbitals at the end of the calculation. Yeah, so we'll set that to 2, just in case we want to see the orbitals, which may come up in the next meeting. But now we have our input, which should be totally set. We can select all of our data, copy it, and then we'll paste it into a Word or a text file. So this is just my text editor. You can use Notepad, it's fine. But we'll paste in our input file, and then we'll want to save it as a .in file. So I have this folder here. We'll save it as published. You generally want to be as accurate as you can with these titles, but not necessarily needed. Just put as much information as useful as for you. So I'll just put published_IQmol and save it as a .in file. So in our folder here, we have our input file, published_IQmol, and it should be ready to send to the server. So yeah, these slides are basically just what I already covered. So I'll send these slides over so you can look at them. And one other thing I do want to cover is if you're using a non-standard basis set, a basis set that's not built into Q-Chem, you can use this website, basissetexchange.org. And it's pretty handy. It'll tell you all the basis sets that are available for the atoms that you choose. So for this molecule, we're going to have carbon, nitrogen, oxygen, hydrogen, sulfur, and ruthenium. And all of these basis sets on the left are available for for the atoms that we selected. So we can see DEF2 SVP is available for these atoms. We'll go ahead and select it. And then we can download or choose the format that we want our basis set in. So you can see Gaussian, you can use Sci4, you can use Orca, but here I guess we're going to be using Q-Chem. So we'll select Q-Chem, and we can get the basis set. So as you can see here, in our variable section, it adds this pure cart equals 1, 1, 1, or pure cart equals 1, 1. If you see this in the basis set that it gives you, you'll need to add this to to the input file. So here I would add pure cart equals 1, and then we would also need to add the basis set. So this basis section, we would copy all of this and the ECP section, and instead of having it specified in the here, we would change these to gen. Gen tells it to look for a basis set at the bottom, and then we would paste it at the bottom here. And we have our ECP section and our basis section. So if you ever need to use a non-standard basis set, that's how you would do it. But we won't need to do that today, so I'm not going to save these changes. Now we have our input file all set up and ready. We'll want to send this to the server so that we can start the calculation. So if you open up MOBA Xterm, when you open up MOBA Xterm, it'll look like this. Just click Start Local Terminal, and you'll be in the terminal. So in order to get into a server, you would use the SSH function. You can log in using SSH, the user, and then the server. So the user for us is Grotjon, and the server is IQmol. So you just type in SSH user at server, and then you can type enter. And the first time you log in using MOBA Xterm, it'll ask you for the password. You only have to type it in once. And then it'll remember it. So after you type in the password, you should be logged into the server. And this is what it looks like when you log into IQmol. So on the left here on MOBA Xterm, you can see all the folders that are in the server. So right now there's only 2 folders, my folder and then a scripts folder, which I've made. So another way to look at this is to use the ls command. So type in ls, and it'll show you all of the files and folders in the directory that you're currently navigated to. One thing that you may want to know is how to the flags. So if you do ls-l, this will tell you not only the folders and files, but the last date and time that they're modified. So this can be useful if you have a bunch of different calculations. You just want to see the most recent ones. You could do this ls-l and find the most recent calculation. So once you're in the server, you're going to want to make your own folder to do your calculations in. There's 2 ways you could do this. You can use the MOBA Xterm create new directory up here, or you can use the command mkdir. So this will make a folder with the name. Let's say I'll just make a folder called test, or I'll make it in mine. So I'll navigate to my folder using cd, and we'll make a directory DFT-test. And now if we ls, we can see our new folder DFT-test is here. To navigate around, to navigate into a folder that you can see, you can use the cd command. So cd space whatever folder you want. So in MOBA Xterm, you can double click to select text, and then you just right click and it'll paste it. So we want to move into this directory, DFT-test, and we can select it. So now we're in that folder. If you want to exit this folder, you could do cd space period, and this will go back up 1 directory. And all these commands are in the slides that I'll send over, so you don't need to necessarily memorize them right away. You could just look at the slides, or online there's tons of different like cheat sheets and stuff you could use. Say you wanted you're in some extended folder base. If you want to just go to the home directory, you can just type cd with nothing after it, and it'll take you to the home directory. Yeah, it can be useful sometimes. But now we want to move our input file to the folder. So I'll just cd to this, cd to my folder, cd DFT test. And if we look at the directory, it's empty. So there's nothing in here. We want to move our file to this directory. Now there's two ways we can do this. We can either use the file navigation on the left. So we would navigate to our DFT test folder, and we can click upload. And this will give you basic Windows, GUI. You can select the file you want to upload, and it'll upload it for you. And now if you do ls, we can see our files in here. But say we uploaded the wrong file, we can either delete it by using this thing on the left here with delete selected file, or we can use the command rm. So I can type rm space the file name, and it'll remove the file. So now we ls, and there's nothing in the directory. Say we want to delete a folder with something in it. The rm command won't work by itself. We have to add a flag. So let's just make a directory here. Hello. Now we have this folder hello. Say there's something in the directory, we won't be able to delete it. But if we use rm space -r, we can remove this folder. The R stands for recursive. It'll recursively delete anything in the folder that you specify. So rm-r hello, it'll remove the folder and all of its contents. One cool thing about all of the Linux commands is that if you do this flag --help, it'll tell you all the flags that you can use and how to use the command. So we did rm-help. It says usage rm option file. So to use the command, we would type rm, then the option, which is one of these flags, and then the file. And it'll tell you all the different flags that you could use. But say we're using a different terminal that doesn't have this, this side pane, we can use the scp command. So in order to use scp, we would open a new terminal and navigate to the directory that our file is in. So I'm going to navigate to desktop, and then navigate to DFT workshop where our file is, and we can see our file here. So to use scp, we just type in scp, then the file that we want to transfer to the server. So here it's published aquo.in, and then we would type in the location of the server. So I want to upload this to Grochon at itcock : and then the directory we want to upload it to. So I can go over to our itcock terminal window, select the folder, and paste it in here. So now we have our scp file to the server space. And we can type it here or press enter here, and it'll upload the file. Hopefully. There we go. It sent over the file, and now if we look in the folder, it's here. scp also works in the other direction. So say we wanted to download a file using scp, we can do scp server name and location / the file. So our file is published _aquo.in, and we wanted to move it to the directory that we're currently navigated to. We can use this /, and that just indicates that I want to send this file to my current folder, and we can type enter, and it'll download the file. So that's basics on using scp. If you want to move a folder, which is actually where SCP is very useful, you do SCP-R and the same thing. So -R again is recursive, and it'll move the folder and everything in the folder. So you can download or upload an entire folder using the flag -R. Alternatively, you can use the MOBA Xterm download. Works the same way as the upload. Yeah, pretty self-explanatory for that. But now we have our file. One more thing with the Linux terminal. Say I wanted to move this file to another directory. Let's say we'll make a directory hello. We can either move the file using mv, the file, and then the folder name. So this will move the file to folder hello, or we can copy it using the cp command. So cp publish _aqua to hello, and we can see our file is still here, and if we navigate to hello, the file will also be there. So we successfully copied it. But I'm just gonna remove this folder, and yeah, that should be everything for using the terminal in terms of navigation and file uploading, downloading, stuff like that. But now we want to know how to start our process. So one command that you should know before starting your calculation is the top command. So top will show you all of the processes currently being run on the server. So as you can see, not very many processes are being run. We have our top command and some basic administrative stuff that's going on. If you start a Q-Chem calculation, this will show up here with the PID on the left here. But because there's no calculations, you can see up here, CPU usage is 0%, 0.2%. That means there's plenty of space for us to add a computation. Try not to make this over 50%. So if the server's being used, it should go up to 50%, and if it's about 50%, you shouldn't start a calculation because it puts wear on the server and it slows down all of the processes. So yeah, as long as you go up to 50%, it should be fine. This server, I think, has 64 processors. So that means we can go up to 32 processors before reaching that 50%, which if it's just us using the servers, should be plenty of space. But if you're in top, you can leave top using Control-C, and it'll put you back into the terminal. Now we want to start a calculation. There's a traditional way using Q-Chem and another way using Slurm. Slurm is not available on ITCOC because Python is not downloaded. I'm going to try to talk with Dr. Cooksey about downloading Python so we can use Slurm. It makes things a lot easier. But we won't be able to use that today. We'll have to start our calculations the traditional way, and next time I'll talk about using Slurm. So we have our file here. In order to start our calculation, we type in Q-Chem space -NT. So -NT means number of threads. So say we wanted to run this on 4 threads of the server. We do -NT4. You can do 8, you can do whatever number you want. We'll just start with 4 because it's reasonable. If we used 4 processors for this calculation, it would be done by probably 3 or 4 days, I would assume. And then if you did 8, it would be half that, so 1 to 2 days probably. But yeah, we'll just do 4, and then we would type our input. So we're specifying the input file, and then we also have to specify an output file. Typically, you want it to be named exactly the same as the input file. So publish_aquo.out, but you can name it whatever you want. But you do have to have this with the .out file. This just tells it to make this file publish_aquo.out, and that's where the data will be sent. One more thing before we start the calculation is we want to add this AND command. If we don't do this, the calculation will still run, but if we close the terminal, the calculation will stop. Using the AND command means that we can leave the terminal and the calculation will continue to run, which is generally what you want. You don't want to be logged into the server for however long, leave your computer on. So yeah, we can avoid this by using the AND command. And if I type enter, we did have an issue. So let's take a look at the issue. Another command that might be useful to know is tail. This tells you the last 10 lines of the file. You can do tail-n to do, say you wanted to see 100 lines of the file. You could just do that and then the file, but here 10 is fine. We'll do tail publish.out. And here it looks like we have an invalid charge multiplicity combination. So this is a good chance for us to use Vim. I won't go into too much detail on Vim because you can get away with never using Vim. Like when I first started, instead of using Vim, I would just modify, go back to my text editor, modify whatever I needed to modify, re-upload it, and then start it again. But Vim allows us to edit the file directly in the terminal. So we'll do vim published_aquo.in, and this will take us into Vim. So Vim is a text editor. It's a little bit different than a traditional text editor because there's an edit mode and a command mode. When you first enter Vim, you're in a command mode and you can't change anything to the file. So if I typed, of course I typed the one thing. So if I type whatever, it won't let me edit it. So to enter edit mode, you just press A and you'll see this thing at the bottom here says insert. That tells you that you're in edit mode. So I think what we need to do is change our ruthenium 2 to a singlet, because I believe that's what it should be. So we had the multiplicity error, it was a doublet. It should be a singlet. We can change this to a 1 and press escape to exit and edit mode. And if we're happy with our changes, we can type :WQ. So this tells us to write and then quit. If you want to just quit, you could do :Q. However, if you make changes and try to do this, it won't let you. If you want to quit and erase any changes you made, you just add the exclamation point. So :Q exclamation point will let you quit and not save changes. But I think we made the changes we wanted. So we'll do :WQ and it'll save. And now if we do head, which is similar to tail, but with the first 10 lines, and look at our file, we'll see that our molecule is now changed to have a multiplicity of 1. So the file should be ready. Chance for another thing to show. History. This is a cool command. If you type in history, it'll show you every command you've ever typed in with an identity of that command. So I want to reperform command number 2031. Instead of having to type it all out, I could just do exclamation point 2031 and it'll redo that command. Very handy especially for the long ones. You don't want to type everything out again. So we'll do exclamation point 2031. It should start the calculation. This time we didn't get an error command, so that's great. If we type enter, it'll take us back into the terminal. We can do ls, And now if we tail our output file, it should show that it's running. So if you see just some random stuff without an error message, that tells you it's running. Alternatively, you can do LSL to show you when it was last updated. So it was last updated 1435, which is right now. It tells us that it's still running. Or we can use top to look at the commands, and we can see that our calculation is running with PID 11724. Say we messed up the calculation, we know it's wrong, but it's running correctly, and we wanted to cancel this calculation. We type in the command kill and then the PID. So if I do kill 11724, 111724 rather, it'll stop the command. So now if we do top, it's no longer running. Useful in certain circumstances. I needed to kill this job anyway because I don't need to calculate it. But typically you would just leave it running until it finishes. So two things that could happen when it finishes. Let's just go through these slides real quick. I have all the commands that I talked about here. So you can look through the slides if you forget. Something I didn't talk about in Vim, you can copy and paste using the Y or P command. Yeah, it's good things to know. Slurm, I'll talk about next time. Starting with calculations, checking the calculation states. Again, use top or SQ once we start to use Slurm. Yes, so when you're checking the calculations, you do tail the file, and you can either see, thank you for using Q-Chem, have a nice day, which means that your calculation completed successfully, or you'll get one of many types of error messages. There will be some detail in their error message that will tell you what went wrong and what you might need to change. Like as we saw before, we had the spin multiplicity error. So this is written in the output file, and you can sort of tell what the error is and what you need to fix. So for example, I have one calculation that's completed successfully here. You'll see this at the bottom. Thank you for using Q-Chem. Have a nice day. Calculation went well. Or you can see something like this, where you see Q-Chem fatal error occurred. Gen SCF man exception, SCF failed to converge. And this means that the SCF number reached our maximum number of terms, 6,000, and it didn't converge. So it stopped the calculation. So from here, you could add something to your file. So if I go to my input file, I have this max SCF cycles equals 3,000. So if it stopped at 6,000, we can make it change to like 10,000. So we go through 10,000 FCF cycles. But it's likely if you go up to something that high, there's another problem. So, 6,000 is probably more than enough than you'll probably ever need. One other thing I forgot to mention is this geom opt max cycles. In a geometry optimization, the default number of iterations it'll go through is 50. And if it doesn't converge in those 50 cycles, it'll terminate. But you can change this by using this geom opt max cycles, say 600, and it'll go through 600 iterations before it terminates. So generally, you do want to change this to something higher because, especially for the more complicated molecules, 50 is often not enough. So that's just something you might need to change. Almost done here. So say we got our successful calculation. To look at our calculation, this is for a different file, but should serve the same purpose. I have my successfully optimized calculation here, which I'll just drag into Q-Chem. Oh. Don't know what that is, but it's fine. So this is a molecule that I've optimized previously, something from my project. And you can see on the left here, it has the title that we gave it with this drop-down menu with a bunch of different data. So we can look at this molecule to see if everything looks correct. We can look at bond distances by selecting two atoms. So say we wanted to know the distance between the ruthenium and this oxygen. Okay, so we have our two atoms selected. Say we wanted to know what this bond distance is between this ruthenium and the oxygen. We select the two atoms, and it should show up in the bottom left. So we have a distance here, 2.20238 angstroms. So you could do the same thing for a bond angle, a dihedral, or whatever. If you want to know what it is, you could just look down, select what you want, and look down here, and it should tell you. If this is hard to read, you can also go to calculation Q-Chems, or sorry, build, set geometric constraint, and it'll show you the same information here. So use that to look at your output files. You can also look at the geometries it goes through during the optimization. So go down to this drop-down menu geometries, and you can see how it changed throughout the optimization cycle. It can be cool. Sometimes it can mess up, and you can see why the geometry messed up at a certain spot. And you can just look through each point. The one at the very bottom is going to be your optimized geometry, and this value here is going to be the electronic energy of the geometry optimization in Hartrees. So this molecule had a value of negative 2,280.75 Hartrees. And then if you wanted to compare this, you would subtract it from whatever other confirmation you have to find the delta G. Actually, delta E of the calculation. If you want a visual of the geometry optimization cycle, you can double click on geometries and it'll show you this graph of how the energy changes throughout the geometry optimization computation. So as you can see here, gradually asymptotically approaches a point, which is what you want. And this tells you that this is going to be the most optimized geometry. Also, in your calculation, you can do display atom labels, and say you wanted to know where the charge is located on your molecule, you can do partial charge, and it'll show you where all the charge is on your molecule. This is a net neutral compound, so there's not going to be charge accumulated anywhere. But if you have a charged molecule, it'll show you where that charge is located. You could do something similar for spin density. And again, this is a singlet, so I don't have any spin density anywhere. But if you have a high spin complex, it'll show you, I have spin on the ruthenium atom, or I have spin on this oxygen, which can be very helpful. So that's under display atom labels. Okay, say we did a frequency calculation. Oh, I didn't get one ready. I can just open up one real quick. So I have this completed frequency calculation. I can drag in the out file. And now it shows my calculation for a frequency calculation. So if you look at the geometries for this, there will only be one geometry because the electronic energy doesn't change when you do a frequency calculation. You can look at all the frequencies though that are optimized. So say I wanted to look at this imaginary frequency, I can see what's happening in this frequency and what's occurring. You'll more want to look at these when you're doing transition state calculations or calculating absorption spectra. But if you just want to see, how the molecule is moving, you can look at all these various frequencies. And this really low energy frequency is going to be this water moving back and forth, or these hydrogens moving back and forth on the water. In order to find the enthalpy and entropy of a frequency calculation, you can't do it through IQmol. You have to look at the output file. So I'll open up the output file here, scroll to the very bottom, and it'll show total enthalpy and total entropy. So this is how you can find the overall Gibbs free energy of a molecule and thus find the Gibbs free energy change in like a transition. So yeah, this is where you'll find those. And in order to find the Gibbs free energy, you'll want to use the equation. The total energy of the molecule is a combination of the electronic energy plus the enthalpy plus the entropy times the temperature. And unless you're doing something complicated, temperature is going to be 25 degrees Celsius, which you would convert to 293.15 K. And just a couple tips that I'll give for performing calculations. Make sure when you run calculations to do everything in a separate folder. If you keep it all in one folder, you'll have all the error files, all the input files, all the output files in one folder, and it can get really complicated. So just make a separate folder for every calculation that you want to do. I kind of go crazy with all the subfolders, but you don't need to do that. Just organize things that works best for you, but at least put each calculation into its own folder. And then one other thing, especially if you're doing lots of calculations, keep track of all of your calculations with a spreadsheet. I'll show an example of a spreadsheet that I used for my calculations. So I have the calculation identity on the left. I have the server that it's running on, and then I have the type of calculation. So I have optimization, frequency, single point energy. If it's green, that means the calculation's done. If it's yellow, that means it's running, and it has the ID that I put here. So instead of having to go through and look at every single calculation, I could just look at the ID, go to the server, type top, see which IDs are still running and which ones are not, and I can very quickly identify which ones are done and which ones are still running. And then, if it's failed, you can make it red or whatever. Just do what works best for you. This is just sort of an example of what works for me. But this is very helpful, especially when you start doing more calculations. And I think that's all I have this time. Sorry, it took a lot longer than I was expecting. But next time we'll talk a bit more about choosing a functional and basis set combination, visualizing various molecular orbitals such as the HOMO-LUMO, finding delta G and activation energy for chemical transformations and transition states, and then finding the potential and pKa of various transitions to use in something like Courbet. Courbet diagram replication. And then also, I'd love to talk about the projects you guys are working on and see if you have any questions and help you out with whatever if I can. But that should be mostly it. Thank you guys for sticking around. And yeah, if you guys have any questions, I'd be happy to answer them. And if not, I'll see you guys next week.